Minasan, konnichiwa, Zamurai Engineer desu. So in this live stream, let us discuss about tension member design. So we will use the document by AISC. So we would like to read it to the AISC, particularly to the author of this teaching module, which is Scott C. Bian of University of Massachusetts, Amherst. Okay, so and this lecture would be brought to you by Dr. AP Samurai Engineer TV channel. Okay, let's start. I would like, before we go on, I would like to test our sound. Please confirm our sound test. Okay, so according to Grande, so it's clear. So let us proceed on our discussion. Okay, so in this discussion, we'll have three different presentation that sorry about that. That is why motors with open pipes should be banned. There is no good about motorcycles with open pipes. Motorcycle is developed by engineers in order to transfer goods and people from one place to another, not to give disturbing sound. Okay? So, sorry about that sound. So, let's proceed with our discussion. It's about tension member again. So we'll present to you different or three different documents that constitutes the teaching modules for steel instruction. So we are using AISC. This document is actually free from the website of AISC. So while we are doing the textbook is what, 2012. By 2012, that is already 10 years old. So this is the latest. So we also need the textbook. We will just supplement by the current practice. That's why I told you that this is AISC 360-16. Okay, this is the current practice. Okay, so let's take a look. So what is a tension member? It is a structural member subjected to tensile axial load. So as you can see, there are two forces that tend to stretch the member, wanting to elongate the member. So the load is stretching the member. So that is usually application for what? Cable and ties, for example. Okay? So we already mentioned so much about it. So we'll just do it, present it, because this is the current teaching module with regards to the code. Okay? So again, strength design requirement, meaning LRFD and ASD. So there are two types according to the code that is allowed. So first, let's mention ASD. ASD meaning alternative steel design, or it could also mean allowable steel design, or it could also mean working stress design. And with that, the equation is supposed to be P sub A must be equal or less than P sub N divided by omega. So we already know what is omega. We already know what is P sub N. Okay? We already know what is P sub A. So P sub A, that is the force allowable must be equal or less than to force nominal. Okay? P meaning force. Okay? Okay? Force of tension, tensile force, okay? Tensile force, okay? And omega, that is our safety factor, okay? And on the other hand, if we are using LRFD, okay, or the ultimate strength design, so we have P sub U must be equal to or less than phi times P sub N. So meaning the ultimate tensile strength must be equal to or less than reduction factor phi multiplied by nominal force. Okay? So phi varies depending on failure mode. So there are several failure modes. So failure mode, tensile. Failure mode, compression. So there are failure modes like flexural, failure mode, torsion. So the value of phi are different from each of them. For example, when we talk of tensile strength, okay, we will have limit state design. Number one, we have strength, limit state. We have serviceability, limit state. So those are the two important limit states. So under the strength limit state, there are 5, but it is only 4 when we are talking of tensile strength. So 4, what are those? Yield, number 1. Yield on gross area. That's why we are talking gross area. We are already talking of net area. That is when we are going to take note of the rupture, where the element would be ruptured. So that's why we are talking of net area, just on the previous module. Okay. Then number 3, block shear. So that is also tensile strength limit state. Okay. And number 4, bearing or tear out. Okay. Tear out. This is pronounced tear out. So there are two words, tear and out. Tear out at bolts. So there are tearing out at bolts due to bearing. So there is a bearing. So all of those 4 are also being given in the board exam, and they are also usually being found on the actual practical application. Okay. So when we talk of that, we will take a look at several tables please prepare your tables, AISC table or NSCP. Either NSCP or AISC. So without that, you can use other commercial table if you want, but for reference purposes only. The actual values are on the AISC and NSCP. Okay. Also, we will give you maybe video, animation, photos to present the failure modes. Okay. And we will tackle different topics on yield, rupture, block shear, and bearing. So these are the 4 different aspects of strength limit state. Okay. So under the theory, we will talk about the theory, and we will also talk from the manual. Manual, there are handbook. Okay, there are important consideration with respect to practical from the experience, from the codes. Okay, so they are written on the manual, and also overview slides, design aids. So we'll have those things. So let's therefore start with our theory. Okay, so what is the theory behind? We already talked a lot about this, but now we are updating our discussion on the latest AISC. Okay. So again, let's proceed on the theory. So let us first. So there are 4 limit states with respect to strength. Okay, we are specifically talking about tensile failure mode. Okay, number 1, yield, and that yield is for gross area. Yield on gross area. Okay, recall yield on gross area. So this is the simplest one to talk about. So you just have to take a look that when a member is loaded, the strength is limited by the yielding of the entire cross section. Okay? Entire cross section. So in this drawing, it is the side view of W section. It's a side view W section. So L0 is our length of the section. So if you multiply epsilon yield times L0, so this is your stress strain curve that would correspond to our tensile force P, which is equal to Fy times gross area A. Okay, so that's the very simple formula that we know about when we are using yield on gross area. So yield strength times the gross area. So this section, since we are applying the force, tensile force, it is subjected to delta. So change in length. So delta is change in length. Okay. So change in length, it would elongate. Okay. So it would elongate. So when the member is loaded, the strength is limited by yielding of the entire cross section. So this delta is actually the total change in length but that is also the total contribution of the total length. Okay, that is the total contribution of the total length, because per unit area there is a small contributing strain per length, per unit length. So if you total the strain, so you have the delta. Okay? And it is affected by the stress-strain condition. Consider, for example, L0 is equal to 100 inch long tension member. Okay? Let's consider, and we have this stress-strain diagram. Okay? So, usually, epsilon at yield, this one, epsilon at yield is about 0.001 to 0.002. That is the usual strain at this point. This what? This is corresponding to the maximum yield. There are two types of yield, maximum yield and minimum yield. So it is corresponding to the maximum yield. So this is about 0.001 to 0.002 strain, meaning inch per inch. Like 0.001 inch per inch. Per inch of unit length, there is a change in length of 0.001 inch. Okay? So 0.1% or up to 0.2% change in length. Okay? What about the stress? Of course, it corresponds to yield. Okay? Yield point. So what do we mean again by ESH? This is the modulus of elasticity E. E is the slope, stress divided by strain. That is the value of modulus of elasticity. How about E sub SH? That is strain hardening part. We are now on the plastic part. This is now on the plastic region. So this is on the elastic region. This is on the plastic region. Okay? So, what are the points? So, usually, the strain hardening would start from 0.01 to 0.3. This line is from 0.1 to 0.3. Again, this line is 0.001, take note, to 0.002. So, this one is 0.01 to 0.03. Strain hardening point. So, this slope. Okay? And the change in length, therefore, would be about what? If the length is 100 inches is the length. We use what? We use the average. I said 0.001 to 0.002. The average is 0.0015 times 100. That is 0.15 inches. Okay? So 0.15 inches. As our total, we are talking now of total. So 0.005, this one, we are talking of per unit length. 0.15, that is total. Okay? So we have, what about at the part? What about at the part 0.01 to 0.03? The average is 0.02. So if the length is 100 inches, so 0.02 times 100, that is 2 inches. So the total change in length is now 2 inches. That is so much. 2 inches change of length of your, that is too much. Okay? That is too much, 2 inches. Compared to 0.15, this is negligible change in length. 0.15. and that is on the what? Yield point. So this point is again 0.001 to 0.002. This is from 0.01 to 0.03, and the ultimate strain is from 0.1 to 0.2, and the rupture 0.2 to 0.3. So remember, recall that diagram. Okay, the common values. Okay, values. So again, when we are going to measure the strain here at the ultimate, what is the strain at ultimate? Why you are using 0.15? Because this point is from 0.1 to 0.2. The average is 0.15 times 100, so 15 inches. Take note of this, 15 inches, more than 1 foot change in length. Okay? We are now on the ultimate, and we are nearing rupture. We are nearing the failure of the element. Take note, the element length is 100 inches. That is too long. 100 inches is about what? 100, yes, 100 inches is about how many? 6, about 6. 6, 7, 9. So, four and 5 is 60. Okay, 5 is 60, 7 is 72. So 9 feet. So 9 feet. No? 9 feet, that is about 10 meters. Okay, that is about 10 meters. Okay, so, and the change is 15 inches. So that is now nearing to the rupture. What about rupture? That is 0.2 to 0.3. So let us compute. 0.2 to 0.3. If you compute 0.2 to 0.3, that is 0.25. So we will compute with our calculator. Let us put on our calculator. Where is our calculator? What happened? Alala. Okay. There. So we have what? So on the rupture, we are going to use 0.2 to 0.3, that is 0.25 times 100. How much? 25 inches. Okay? So, are we clear? Do we follow? So, at this point, we have what? 0.15 inches, then 2 inches, then 15 inches, then 25 inches here. Now, 25 inches, then the element would break. That means ruptured. Okay? Breaking point of our element. So that is the necessary concept that we need to understand. Okay? And for example, we have this as our summary. Okay, summary. Yield, change in change in length, 0.172. Okay, take note, 0.172. We use what? We use 0.0015 because yield is from 0.001 to 0.002. But here, the actual is 0.00172. Take note of that. Okay, if you can go back, we use what? 0.0015 here at the corresponding to the yield point. Okay? But actually, that is not precisely exactly at the point of yield. So at the point of maximum yield, we have 0.172 inches. So for the strain hardening, onset, what do you mean by onset? Start. That is the start of strain hardening. That is 2 inches. So meaning, if your 100 inches length member stretch up to 102, 100 to 102, there is a 2 inches increase in length. That is now the start of strain hardening of the material. Okay, while if the increase in length is 0.172 for the total of 100 inches length, so that is the part wherein we are on the elastic region. Still, we are on this elastic region. And if we are 15 inches additional length, so meaning the total length now is 115, right? So we are now on the peak or the ultimate, right? So what do you mean? Is that excessive deformation defines failure for tension member yielding. So can you expect somebody to feel safe with that condition? No. 15 inches elongated cable, for example, you will not feel safe with that. Okay? Okay, sorry. So, you cannot feel safe about that. So, that means yielding of gross area is a very important strength limit state when we are talking of tensile failure mode. Okay. Now, let's go to the manual. Okay. So, let's start. I was not able to show you the calculator. Okay. You did not able to see the calculator. However, let's now proceed to the manual. Okay. So this is now the 15th edition AISC 360-16 manual. It's now the code. What can we find out? So let us now start to discuss the contents of the code. So tension members. There are chapters about this, chapter B, D, J, and part 5. What are those? Part 5, very important because those are design charts. So, your copy of the AISC 360, look at part 5. That is the charts and tables. Okay. So, chapter B, gross and net areas. So that is for yielding because we are using gross area. And the next topic, we will use net area. That is for rupture. Okay. So now, currently we are using all of this material. If you go to chapter D, tension member strength. Okay. And chapter J, block shear. We will also talk about that. So block shear. Okay. So, gross and net area. Okay, where we can find it. Section B 4.3, you can find the criteria. This strength criteria, again, when we are talking of strength, that is chapter D, design for tension members. Okay, so those are specific location of code provision in our manual. Okay, so we are talking about what? Gross area, net area, block shear. Okay, so we can what? Use 0.9 for yield failures. So yield is a failure mode. Okay, too much yielding. Okay, as we already shown on the theory. Okay, on the theoretical discussion of concept. There is too much yield, we can say it fails. Okay, so yield on course area, we are using what? Phi sub t. So phi sub t meaning tension. Phi sub t, phi is tension. Okay, that is 0.9. We have to use 0.9. That is for LRFD. For ASD, we are going to use omega sub t is equal to 1.67. Take note of this because these are supposed to be memorized. These values are supposed to be memorized. When we are talking of rupture, phi of t is equal to 0.75. Phi of t, phi of tension, 0.75. What about omega sub t is equal to 2? That corresponds to one another. We can actually determine one if the other is given. Okay? So because pi, okay, is equal to what? Pi is equal to omega over 1.5, I think. Okay? So can we do that? Or pi is equal to 1.5 divided by omega. So that is the relationship. Okay? So 1.5 divided by 2, that is 0.75. 1.5 divided by 1.67, that is 0.9. Okay? So the relationship is, how what about block shear? So when the failure is for shear or block shear, that is 0.75 also. So rupture on effective net area 0.75. Block shear also 0.75. Okay, take note of these values. These are coming out from the code. Okay. So now let's look at the first. So we are talking about what? Four different strength limit states. So number one is yield on gross area. So what about yield on gross area? So we have the following formula. This is the summary. This is written on the code. Actually, the equation number is on the code. Chapter D, equation D2-1. This is our formula using gross area times yield. That's why yield on gross area times yield. We have the following, and gross area, the total cross-sectional area in the plane perpendicular to tensile stress. Take note, perpendicular to tensile stress. This is a very important description of this area. Okay? Any question? Any question about this? Any question? Do we have any question? Okay, again, let us move on to the next discussion, which is on the following live stream. Okay, if there are no questions, we will get out of this live stream, and I expect to see you on the next live stream. Okay, so therefore, we should be able to cut off at very important specific topics. Okay, you have to separate one video from another. Okay, again, this is Dr. AP, preaching engineering for nation building.